Hello, students. So I would like to talk about something we haven't done much, but something that people think, well, people often think that's all there is to linear algebra is systems of linear equations. So I'd like to talk about systems of linear equations with you guys a little bit, or just really in the context of the fundamental theorem of linear maps, because this theorem can say something about systems of linear equations. Now, I didn't want to have you guys watch me write out all these indices because there's a lot of them, so I wrote this out ahead of time. Now, suppose we have a system with m equations and n unknowns. We could always write it like this, where we have capital A's being our scalars, x1 through xn is our variables, and we have m different equations because we have coefficients of x to the I, and then we have j different equations. I have to use double indexing here. I know, not everybody's favorite, but really the only way to do this sensibly. So how could I apply the fundamental theorem of linear maps here? Well, what I could do is I could say for any x1 through xn, I could have a map where the output is the left-hand sides. So not this, just the left-hand sides. So how many inputs? Well, we have n inputs. We have m outputs because each equation is going to be a possible output. So basically we have a map T from V to W, and the dimension of V is n and the dimension of W is m. So let me ask, what if we have more equations than unknowns? So this would be m is greater than n, because m is our number of equations, and n is our number of unknowns. So if m is greater than n, well, what do we normally think? Well, we think too many equations for the number of unknowns, we might not be able to solve this. However, because if we let the right hand be 0, we could always let everything be 0 and we'll get 0 as a solution. So what can we actually conclude? Well, we can conclude that let's look at this again. We could conclude that we could replace the coefficients on the right so that there are no solutions. So I'll say some coefficients for the right-hand side give a system that is not solvable. Okay, well, let's think about what's going on here. We said that m is bigger than n, right? So that means m is bigger than n. And what did our fundamental theorem say? It said that the dimension of V equals the dimension of the null space plus the dimension of the range. But you know what? I shouldn't have even written that because we've already proven something else. We've said that if T is a map from V to W and the dimension of W is bigger, this implies T is not surjective. So that means there's something in W that does not get hit. Okay? So we could let alpha 1 through alpha m be, well, I shouldn't say the because there's usually more than one, but I'll say an element not in the range of T. And we know that there's not going to be any I'll call that alpha. There's not going to be any V that hits alpha. Okay. So that's if we have more equations. What if we have fewer? Well, here, the dimension of V is greater than the dimension of W. And what do we know? Well, from our result, we know T is not injective. T is not injective. So what do I know? Well, we know T of V1 equals T of V2 for V1 not equal to V2. Lots of ways I could do this, but what I'm going to do here is I'll move this over to the left. We've sort of done this before, but I'll just redo it to show you how we get this. Okay, well, I know that this is non-zero, and it goes to 0. How do I know this is not 0? Because V1 is not equal to V2, and the only way that V1 minus V2 is 0 is if V1 and V2 are equal. So what does this tell me? I have something that's non-zero going to 0. So I know then the homogeneous system has non-trivial solutions. Not just 0, but other solutions as well. So that's a nice way that we can use the corollaries to the fundamental theorem of linear maps to make some statements that we know about homogeneous equations, or just systems of equations in general. What did we say? We said, hey, if we happen to have more equations, too many equations, then we can get ourselves into trouble. There's something on the right-hand side that we don't hit. If we have fewer equations, what do we know? Well, we know that there's non-trivial solutions. There's not a unique solution. And this usually takes a bit of work in a linear algebra class. This comes right out of those injective and surjective proofs, and those proofs came directly out of the fundamental theorem of linear maps. So we got a lot of mileage out of that theorem already. And I guess that's a good excuse for calling it a fundamental theorem.